All right, let's get started. So what we'll do is we'll get started on talking about vibrational spectroscopy, and then we'll pause midway through. I'll pass out the exams. You guys can take some photos of it for your later study, pass those back in, and then we'll finish up with the vibrational modes of acetonitrile. So this is this week's lab. You're in the lab taking infrared spectra of benzene and chlorobenzene. You're looking at the symmetry of those vibrational modes. We'll talk about those today. But just in general, I want to talk about vibrational spectroscopy. You know, up to this point in the course, our theoretical model has been the particle in a box. And this time we're going to talk about how many vibrations a molecule can have. And each one of those vibrations, there's 3n minus 6 of those. If you'll remember the cartwheel lecture, where we had 3 translations, we had 3 rotations for a nonlinear molecule, and then everything else was a vibration. If you think about those vibrations, we can describe them in one dimension. Even the movement of my elbow, there's a whole lot going on in all 3 coordinates, but you can break that down to just one angle. And so that can be one coordinate. And if that's a spring, if it doesn't want to stretch too far out or too far in, there's a midpoint where the force is 0. And we can treat that like a harmonic oscillator. We can have a parabolic potential energy function. Instead of the particle in a box being 0 potential and then infinite potential at the walls, what if it was a parabola? Then we would have harmonic oscillation. And we treat every vibration in a molecule as a harmonic oscillator with a parabolic potential and a single dimension. And you might say, does that really work? Yeah, it really works. So we can take all of the complicated motions, even like a twisting motion, and describe that with one dimension of the twist angle. And so every motion in an object can be described in one dimension. Now, it might be very complicated. There might be a lot of things moving, like the symmetric stretch or the asymmetric stretch. You have all of those bonds stretching and compressing, but you can take their equilibrium position and say, okay, go one direction from equilibrium, and then come back to equilibrium, and then go the other direction. And so difference from equilibrium is the dimension that we'll have. And so we have 3n minus 6 vibrational dimensions, but you can think conceptually as 3n minus 6 particles in a box. And all of those energy levels. So what that means is you have a lot of fundamentals. You have 3n minus 6 fundamental transitions. And then think of all the overtones and hot bands. Luckily for you, though, in infrared spectroscopy, we're not going to see the hot bands. Things aren't hot enough. Okay? We might see an overtone. They're going to be really small, as you saw from the particle in the box. We are going to get some complications in what we call combination bands. And this would be 2 vibrations that kind of talk to each other. And they can combine in plus and minus ways. So there are some combination bands which are also pretty small. But mostly what you see in an infrared spectrum are the individual fundamentals of every different vibration. So let's just sort of the mental framework to go from the particle in a box now to 3n minus 6 particles in a box. 3n minus 6 fundamental vibrational modes. Sometimes it doesn't go, and now it goes like 20 clicks ahead. Okay, so let's go back. Okay, so we're talking about vibrational motions, and I talked about that harmonic oscillator potential. Well, we have that equilibrium distance. And now it's very simple to think about that as a bond distance. So we'll talk about R, like the radius or the distance between 2 atoms. But it could be something complicated like multiple stretches and bends all combined. But the main point is you have an equilibrium position. It could be the equilibrium position in Cartesian coordinates or in spherical polar coordinates. But you have some set of coordinates that's the equilibrium set. That's the minimum of the potential. And then you're looking at a difference. So that difference can be, smaller numbers or greater numbers, but it doesn't matter in the potential because it's that difference from the equilibrium position squared. And so the potential goes up on both sides, and it's a parabola. Then the restoring force, the thing that pushes it back downhill, is the steepness of that parabola, and that's the force constant. That's K. So this is just like Hooke's law in your classical mechanics course, your physics course. So this is just regular harmonic vibration. So a mass on a spring. And even though that's sort of a classical, macroscopic model, it really does work well for vibrations. Now that force constant is in newtons per meter, so that's how many newtons it takes to stretch that coordinate 1 meter. Okay, these are pretty strong force constants. And we end up with this parabolic potential energy surface. That's the one shown in blue up here. Now it works pretty well down here at the bottom where there's very small displacements from the equilibrium position. But we know, let's just think of a bond stretching. If you really pull on that bond, the spring starts to get weaker and weaker and you start to pull the atoms apart. Okay? And so that's called anharmonicity or anharmonic potential. What does the an mean? It means to negate it. So it's harmonic potential is the parabola. If you start to stretch that bond too far, it starts to break and you get anharmonicity. And if you compress the bond too far, it's really difficult to see on the screen probably from where you're sitting. But there's two lines here. The blue line is on the left and the black line is on the right. Because in reality, if you push the atoms too close to each other, the nuclei start to see each other. And they repel each other more than the harmonic potential would. And so it's a little more repulsive on the short distance side and a little less attractive on the long distance side. But down here at the bottom of the potential well, the harmonic oscillator is a pretty good model. And it matches what real molecules do. And since most of the time we're dealing with fundamentals, we're just going from that V = 0 to V = 1 state. And that's going to be governed mostly by the harmonic potential. And we're going to see very little anharmonicity in that first position of that first peak.
You said at a certain point it gets to where they repel more than they can be pushed together.
Yes, and you can see that if you were to zoom in on this figure, if you have it on your computer, the black line is on the right. And so the black line is showing you the more realistic potential. And so it repels a little more than what the harmonic oscillator would predict. So looking down here, we see it's a pretty good match for the fundamentals. And so this is zooming in on that small region where we have the wave functions for vibrational motion. Notice the potential doesn't go up straight like the particle in a box. The particle in a box is a flat bottom and then hits the wall and the potential goes to infinity immediately. These potentials still, in theory, go to infinity, right? The harmonic oscillator does. But it goes gradually. It's a parabola. Remember also in the particle in a box, the energy levels were not equally spaced, right? They went up by n squared. So if you raise the quantum number from 1 to 2, it went from 1 squared to 2 squared, 4. And then the next one was 3 squared, 9. Okay, then 4 squared, 16. So it was a big jump as you got higher in quantum state. That's what you had with vertical walls. What happens if I spread those walls apart? The energy level is crushed down because length is in the denominator, right? You'll see nods on that one. Okay. Well, this one, the walls spread out as you go up. So if you kind of think about it, L's changing with each quantum state. And because L's getting bigger and bigger, the energy levels drop down, and we see equal spaced energy levels. So that what used to be a quadratic dependence on quantum number has now dropped down to a linear dependence on quantum number. So if I go from V = 0 to 1, I get 1 unit of energy. V = 1 to 2, same unit of energy. 2 to 3, same unit of energy. And that unit of energy is the vibrational frequency in wave numbers. So this is super easy to think about. The difference in energy level is the vibrational frequency for that motion. And so that fundamental transition will be located at the vibrational frequency in wave numbers. And if you plot it versus wave numbers, you can read the vibrational frequency right off the chart. So if a CH stretch vibrates at 3,000 wave numbers, that's going to be the location of that peak. That's the difference in those energy levels. It also means the hot bands will be right there at 3,000. And so even if you had a hot band in there, it wouldn't be at a different location. It would be right on the vibrational frequency. Let's see what else we can say. So this is just showing you the energy equation. HC new in wave numbers, the HC just converts it from wave numbers into joules. And it's times V plus 1/2. So it's a little particular in this font that I have on my computer. This is the Greek character nu, and this is the Greek character V. So this is the vibrational quantum number, V. And this is the Greek character nu. Oh goodness. Okay. So the vibrational frequency is traditionally given the Greek character nu. And the vibrational quantum number, all through the particle in a box, we used N. Okay, but for vibrational quantum numbers, we'll use V. And then later when we get to rotation, we'll use J. So J will be our rotational quantum number. So, and also a difference from the particle in a box. The particle in a box, the ground state was N equals 1. But for vibration, it's 0. V equals 0 is the ground quantum number, ground state quantum number. Then we have V equals 1, 2, 3, 4, etc. So they're equally spaced. Can you look at these and tell me the symmetries of them? So what's the symmetry of the ground state? Even or odd? Good, I like to hear all those voices. Right? How can you get it that fast? It just looks the same on both sides, right? And what about V equals 1? Because the left side is positive. So let's see. The left side is negative, the right side is positive. Okay? They have the same shape, which means they're equal magnitude on left and right, but different sign. And so that's the definition of an odd function. V equals 2, goes up and down, and then back up. Okay? So it's even. Even though there's negative regions and positive regions, they match each other. You can just look at that middle line and see it's symmetric on both sides. And this is part of why I wanted to shift that particle in a box wave function so it was centered on 0, so that you could see the symmetry. And then this one is centered on 0, so you could compare them very easily. So I just wanted your thinking to be thinking symmetry around 0 and to be able to recognize that. So when we got to vibrational wave functions, it would be obvious. And so we have those even, odd, and it alternates just like the particle in a box. And so light is odd. And so if we were trying to go from even to even, that would not be allowed. Okay. And so that would be even times odd times even would equal 0. Whereas any change from even to odd or odd to even would be allowed. So we have an even ground state, odd light, odd excited state, and so that would be non-zero. So our selection rules allow us to have delta V equals 1 and 3 and 5, just like the particle in a box. So if we look now at this region where the harmonic oscillator fails, the anharmonicity region, let's look at that area for a little bit. Okay, so this is the harmonic potential is in yellow, and the anharmonic potential is in red. And I've shown all of the energy levels there for the anharmonic potential. Notice if you think about the bond length for the harmonic oscillator, it's right in the center. And the center is going to be the middle of that potential all the way up. And so the bond length doesn't change with excitation. But for the anharmonic potential, that bond length is going to be halfway between the turning points. So these edges here, we call these turning points. So like this is the long turning point, and this is the short turning point. If you're thinking about a mass on a spring, oh boy, that's a bad spring. Okay, so this is my spring, and it's connected to a bigger mass. So this might be like a chlorine and a hydrogen for HCl. And so that hydrogen is just oscillating. Where does it stop and turn around? It turns around at the edges of those potentials. Okay. And so when we're way up here, what's my bond length? Well, it's halfway between the turning points. And so here's the H. Notice how the bond length has stretched a little bit. As we excite it vibrationally, it spends more of its time away from the nucleus. If we excite it even to higher energy levels, eventually we reach an energy level where the hydrogen stretches and doesn't come back. And the chlorine's like, where have you gone? And off it goes, because it's extremely hot. If you were to heat it up and cause thermal excitation way up there, especially for a hydrogen, 3,000 wave numbers, room temperature is about 200 wave numbers. So we're more than 10 times room temperature. Room temperature is 270 Kelvin. So we're at 2,000 Kelvin. Yeah, let's see, 10 times, yeah. 2,700 Kelvin. Just to get to the next excited state, okay? Stretching that thing out, we'll be at, thousands of degrees, tens of thousands of degrees. And so that is enough thermal energy to drive the hydrogen off of the chlorine. Some other things to note here, these are the dissociation energies. So how much energy would it take to drive that hydrogen off? It depends upon where you put zero. If you put zero at the bottom of the potential energy surface, that would be dE, subscript E. And this is important to take note of for the labs. And so there's a difference between dE and D0. Go ahead and write that down in your notes, the difference between dissociation energies. So when there's a subscript E, that's to the bottom of the potential well. And when there's a subscript 0, that's to the V = 0 state. They're not that different, but it's significant in the lab. The difference is 1/2 of the vibrational frequency, because that when V = 0, what's the energy? It's V plus 1/2 times that vibrational frequency. So it's 0 plus 1/2 times that frequency. So it'd be 1/2 of the vibrational frequency would be the difference between these two.
I'm sorry, for DE, what did you call it, the bottom of the what?
Potential well. So this potential, it looks like a well, like you've fallen down into a well. It's an energy well. And so if you set 0 down here at the bottom of that well, then the distance from that point to the dissociation limit is dE. And then if you're at V = 0, which is really as low as you can go in actuality, you can only go to the V = 0 state. That's the actual dissociation energy. So, but we can write this relationship D0 plus 1/2 nu, these are all in wave numbers, is equal to dE. So dE is slightly bigger than D0. What is the observational evidence or result from seeing anharmonicity? It's a reduction of the vibrational frequency, because you notice the spacing, the levels get closer and closer together. And so if I have, say, a 3,000 wave number fundamental, the next difference will be a slightly less than that. It might be 299, and then 298, and then 297. So those spacings get smaller and smaller as you go up, and those would be the hot bands. And so the hot bands would be sort of sliding to lower wave number values, and so our peaks would become asymmetric. And so that's what we would see in the spectrum. We might see a vibrational peak, and then in a really hot spectrum, those vibrational peaks would be tailing to low wave number values because of the hot bands. and we would start to see anharmonicity. If we had super high resolution, we would see individual peaks on the low frequency side due to those hot bands. And we could assign them. And we could learn more about what this potential energy surface was in actuality, how strong that bond was, what the dissociation limit was. So we're going to actually do some of those calculations when we get to the iodine lab. That's our 8th lab. It's the last one. So we have the harmonic oscillator. This is sort of a review of the equations. We have the energy equation up at the top. Now, if we took that energy equation, anytime you see an energy equation, you need to be ready for me to ask you, what's the transition equation? So could you take that energy equation and come up with the transition equation for all delta V equal plus 1s? Right? So you take V, wherever V is, you put V plus 1 in there and then subtract the energy equation with V in it, and you do the math. It's really super easy on this because V is linear, and so it's just going to be whatever the slope of V is, and that's the vibrational frequency. But anyway, you can prove that to yourself by taking that energy equation and solving for the transition equation. And that would be suitable for the homework, like if you did a Blackboard discussion post for that, would be the transition equation for the vibrational frequencies. Then the frequencies are dependent upon the mass and the force constant. So here we see, again, the solution of Hooke's law. But you have the force constant here in newtons per meter, and then you have the mass in kilograms, the produced mass. And that's a complicated formula. For diatomics, it's pretty easy, but for anything other than a diatomic, ooh, it is a hot mess. Because if you think about even the asymmetric stretch for water, when I was doing my head is oxygen, my hands are hydrogens, and it's doing this, think about all the masses that are moving. We have hydrogens moving away and towards the oxygen's moving as well to keep the center of mass still. And so we have 3 atoms moving, but it's not just the sum of those masses. It's a very complicated formula when you get to something other than a diatomic. So if you're ever asked to solve for the frequency of something, I'm probably only going to ask you for a diatomic because of the reduced mass. And the force constant's really difficult too. It's not just the bond stretching, it's also that oxygen moving a little bit. What's the restoring force on that oxygen's position? And then if you do get into the higher order terms, like we will in the iodine lab, instead of coming up with a brand new model, this anharmonic potential, and trying to solve for that, they just add higher order terms. They just treat it like a polynomial. And so you've got a linear fit, and up here at the top it starts to curve off a little bit, and you're doing Beer's law. What do? You just add a quadratic term in there. Okay? And what do you call it? Well, it's just the quadratic correction. Here we call it an anharmonicity constant. So we're just adding in some anharmonicity. So we're subtracting a little bit that depends upon the quantum number squared. So if it was a linear trend and we want to dip it a little bit and make it nonlinear, we subtract a little bit because the anharmonicity is a subtractive piece. Those energy levels get closer together. And so we put a coefficient in front of it, this XE term. And we go ahead and scale that anharmonicity by the vibrational frequency. And then it's V squared, V plus 1/2 squared. So that's the negative correction for anharmonicity. But if those corrections typically overcorrect, and so then if we really want to be exact, we add back in a cubic term. So this is the YE term. I'm not sure if I've ever seen data that was detailed enough to need a quartic term, but you would just subtract then a ZE term and put V plus 1/2 to the 4th power. And you just keep adding a higher order polynomial to really get the data to match. And then you would record from the fit of the data what XE and YE and in that crazy sense ZE would be. And you can find tables of those values where they've been done for small diatomics. So we will have the XE term for the iodine molecule because we'll get a lot of vibrational measurements on iodine. And so you will be able to look up some of those diatomic data in the literature. And so here are some of the constants we've talked about. We've got diatomics on the left and vibrational frequencies and equilibrium bond lengths and picometers, and then force constants in newtons per meter, and then rotational constants, which we'll get to next. We're not going to talk about rotation today, but the rotational constant is super important. And then we have D0, the dissociation limits from the V equals 0 state. Okay. And so let's look at some of the units. So that's force constant is a newton per meter, and so we have that kilogram meters per second squared and meter to the -1. And so whenever we're doing this math, 90% of the problem is in units. And so when I see force constant up here, and that's newtons per meter, I know inside a newton is a kilogram. And so that tells me that my reduced masses need to be in kilograms. So if I go to the periodic table and I grab the mass of hydrogen and chlorine and I calculate the reduced mass for HCl and I have it in grams per mole, that's not compatible with this formula. So you got to get out of grams per mole and get into kilograms. Simplest thing is to divide by Avogadro's number, okay, and that'll shrink it down to where it's now the mass of a particle, not a mole of particles, but it's still in grams, and so then you just add in that 10 to the 3 to get out of grams and into kilograms, and then you have the number that can be used in this equation. So 90% or maybe 80% of the PChem problems are just figuring out the units. This is going to give you inverse meters when you take all of this, because if you look at the meters, let's see. No, let's see, the meters are going to cancel. That's right. And so then you have this factor of the speed of light in front. And so if you just use 3 times 10 to the 8 meters per second, it's going to cancel with the second, but we're going to end up with inverse meters. And so if you want wave numbers, which is indicated by this little tilde on top, which is inverse centimeters, you're going to need to use the speed of light in centimeters per second. 100 centimeters per meter, so it's 3 times 10 to the 10 centimeters per second. And that's also a place where you make most of your mistakes. You say, okay, it's 3 times 10 to the 8 meters per second, and you go the wrong way. You do 10 to the 6 centimeters per second. You just went the wrong way, and now you're 4 orders of magnitude off. Okay, so try not to do very much in your head, because your head is going to make mistakes. Write it out and convert those things. Okay, in terms of the energy, the vibrational frequency is in wave numbers, which is inverse centimeters. Speed of light, again, you're going to use centimeters so that the centimeters cancel, and then Planck's constant gets rid of the per second and gives you joules. So whenever you see HC nu tilde, that HC is just there to convert it to joules. If you're going to work in wave numbers, you don't need that HC. And so I see a lot of people really work themselves all over the place, converting to joules and then converting back to wave numbers. And if you're going to be in wave numbers and you're going to stay in wave numbers, then don't stick that HC in there. You have the option. All that HC is doing is just converting your units. Okay. And so if you want to work in joules, great. Put Planck's constant in there and the speed of light. But if you're going to work in wave numbers, don't. Just use those constants to convert your units around. And then the rotational constant we're going to get to later, but again, it's another unit analysis. And it'll help you realize when you need your masses in kilograms and what version of the speed of light you need to use. So let's look at force constants. There's a couple of different systems. Have we talked about the CGS system? No? Okay. So this is, I guess, the first place in the course where the CGS system pokes its head up, okay? There are 2 SI systems. So System International, the International System of the Metric Units, and we have the MKS system, which most of us use all the time. That's meters, kilograms, and seconds. That's what MKS stands for, okay? But there's also CGS, which is centimeters, grams, and seconds. It's still distance, mass, and time, but we have different names for these different units, systems. So you've heard of newtons, that's the MKS unit of force, but a dyne is the CGS unit of force. So when you hear dynes, we're talking CGS. And so those two definitions up there, again, F equals MA, so force is mass times acceleration. The mass can be kilograms or grams, and acceleration is meters per second squared or centimeters per second squared. And so a dyne is a force in the CGS system, and a newton is a force in the MKS system. The reason I bring this up now is because you will see in tables the force constant in millidynes or dynes per centimeter or millinewtons per meter. And so I wanted to show you the unit analysis on how to get from newtons per meter to see how many dynes per centimeter that is. And so here's all of the different unit conversions. I know a newton is a kilogram meters per second squared per meter, so newton per meter is that. And so we're going to get out of kilograms and into grams. Okay, and we're going to get out of grams and into dynes over there. So then we have meters canceling. We're converting those to centimeters. And so we have lots of centimeters canceling, lots of meters canceling. And so we end up in seconds squared canceling. So in the end, we have newton per meter is the same as a dyne per centimeter. Times 10 to the 3, because the 10 to the minus 2's cancel. And so if I take that 10 to the 3 and move it to the other side, I have a millinewton per meter is a dyne per centimeter. So this is your conversion for any of those tables that you'll see. What's interesting is sometimes you'll see one source and it'll be dynes per centimeter in that table, and another source will have millinewtons per meter and the numbers are the same, and you're like, oh wow, it must be the same unit because I have the same number. The decimal place is in the same spot. Okay. Yes?
I don't know if this was the answer, but I was getting wondered what do MKS and CGS stand for?
It's just the initials of meter, kilogram, and second. Yeah, and centimeter, gram, and second. Now, what's the unit of energy in the MKS system? It's the one we've been using all of this time. Joules, okay. Have you heard the one in CGS? Erg. E-R-G. Okay, so energy, MKS is joule, and CGS is erg. Now, you've heard that word erg a lot. You just don't know that it relates to energy, but you've heard of ergonomics. And so when somebody comes in and sees that your mouse is way over here on the desk and you're leaning like that and you're clicking, like Dr. White's mouse was always like, I don't know, up by his monitor. I was like, dude, why don't you put that over here where your hand is? But no, he's always reaching over here clicking. And that's an ergonomic nightmare. Okay, what does that have to do with ergs? Well, the energy is required to hold his head up while he's leaning for his mouse and look at the screen is not good on his neck. He's putting a lot of force on his spine. Okay, and so that's what an ergonomic person does. They come and they watch you work and they go, this is not good. And some companies, like the company I worked for before I came here, they paid people to come around and observe you in your workspace, and they would change your whole desk and everything. Like this person came and said, hi, I'm so-and-so with the industrial hygiene and whatever department, and I need to observe you work. And I was like, I'm typing on a computer, you know, what do you need me to do? It's like, yeah, you just do your thing. And so they're looking at me and everything, and they're writing all these notes, and they said, okay, well, you've got a keyboard tray, and that's good, but your desk is like 2 inches too short for you. And so they came in and they like readjusted my desk and everything, and it was ergonomic. So I'm off track a little bit, but erg is the CGS system of units. And then whenever you have delta H, this is kind of going back to, oh yes, question.
Going back a little, did it help?
I couldn't tell with the desk height, okay, but the keyboard tray is golden. I mean, your elbows should be at about a 90-degree angle when you're typing. That's the most comfortable, okay? And so if your desk is wrong to where that keyboard tray can't be at that angle, then eventually it's going to bother you. Okay, it may be way eventually, like years ahead, you start getting carpal tunnel or whatever, but those kinds of repetitive tasks, typing and mousing, do weigh on your joints and things. So, the company thought it was worthwhile with about 3,000 employees to hire a person to go around and make sure that insurance claims for carpal tunnel and those kinds of things would be a minimum. That person would probably pay for their position and make people's lives better, So that was great. The erg part, what is negative delta H in an experiment? What do we call that? Exothermic, right? So enthalpy is heat, that's thermal energy, exothermic. But delta G, we never really taught you that. So with a negative delta G, we say, it's spontaneous. But it's also exo something, it's exergonic. And so you hear the word erg in there. So exergonic would be a negative delta G. Endergonic would be a positive delta G. So this little erg pops up occasionally. It shows up in dynes whenever you have force. And you heard a dynometer, so when you're measuring the torque in automobiles. So then we have these force constants. What do you notice about these force constants? I'll put a few up here just to kind of show you. So the bonding, we've got a single bond for fluorine, 470 newtons per meter, oxygen, 1,100 and close to 1,200, and then nitrogen, 2,300. So even though I said those little sticks in between the nuclei are fake, they're just sort of a mental tool for us to use, there is more bonding going on in nitrogen than there is in oxygen than there is in fluorine. We'll get these same kind of bond order answers from molecular orbital theory. And so how can we say one's right and one's wrong? We'll talk about that in the last part of the course. So that's the part where you go, dang, I've been lied to. Okay. But what is CO? And that we'll cover that also when we get to molecular orbital theory. I mean, it's kind of in between. Is it a double bond? Is it a triple bond? And so I'm just going to leave that question mark there for now. We'll come back to that when we get into the molecular orbital theory. So these are all fundamental transitions in the harmonic oscillator. Delta V is plus or minus 1. So 1 to 2 is a hot band this time. So think about that. The things you memorized with the particle in a box, where you said the fundamental is 1 to 2. Yes, for the particle in a box. For vibrations, the fundamental is 0 to 1. So I don't know how hard your categories are in your brain, But if you've said fundamental is 1 to 2, that only applies to the particle in a box. It's ground state to first excited state. That's the concrete definition of a fundamental. Ground state to the first available excited state. And so in this case, the ground state is 0, V equals 0, so the fundamental is 0 to 1. The hot bands start at V equals 1, go to 2, 2 into 3, 3 into 4. Okay, you still have overtones. Now, anharmonicity breaks the symmetry a little bit. And so with anharmonicity, you can start to get the 0 to 2, 0 to 3. You can start getting those overtones. Otherwise, you wouldn't have any overtones in a harmonic oscillator. But with anharmonicity, the symmetry is broken a bit. They're going to be low in terms of intensity. And those overtones show up if the CH stretch is at 3,000 wave numbers, that overtone would be at 6,000 wave numbers, and that's beyond what we see in our spectrum. So that's in the near infrared. So the mid infrared is what we're dealing with. The near infrared is near to the visible. And so we might see some of those overtone spectra near the visible. So 0 to 2 is the first overtone, 0 to 3 is the second overtone. If you took in the anharmonicity and solved for the transition equation for that first overtone, this is what your result would be. If you didn't use the y value, but just the x value of anharmonicity, this is what you would have. And essentially, it's mostly this number. This is a big number. 2 times the vibrational frequency. Because if you think about the harmonic oscillator potential, it's just 2 jumps. And each one of those jumps is new. And so if you have 2 of them, that's going to be most of the number. It's going to be a small amount subtracted from that. So it'll be slightly less than 6,000. If I go from 3,000 and the overtone's at 6,000, that's the predicted place. And I go there and look around 6,000, and I find one at like 580, 5,800. And so that would be, I would probably identify that as that first overtone. It's not going to be right at 6,000. It'll be slightly less because of this piece here. And so the samples, of course, you can get infrared spectra from solids, liquids, gases. IR is such a strong effect, this infrared absorption, that thick or concentrated samples will absorb all the light. If you think about that, it's just mostly heat. And so substances are going to absorb heat in their vibrational motions. Now, when we get to Raman, we're using a visible laser, and they are very powerful if the sample absorbs. And so a lot of your samples catch fire when you're taking Raman spectrum of them. So you got to really worry about how much laser energy you put into a colored substance that's going to absorb that wavelength of light. You really want the Raman not to be absorbed by the sample, but to scatter. Because remember, Raman is a scattering effect, not an absorption effect. And so your samples, I've caught several samples on fire with taking Raman. And some samples that you wouldn't think would absorb that much. One was just white paper. I tried to get a Raman spectrum of white paper just out of the printer, and turned on the laser, and smoke just started coming out. Whoa. Now, I had it on a little translation stage where I could like move it around, and it wasn't fast enough. Sometimes if you can move the sample, you can get Raman scattering, and the heat is dissipated because you're moving the sample, but I couldn't move it fast enough. So I had it going in a little square pattern, and I mean, it was tiny, like 1/10 of a millimeter. So 1/10 of a millimeter, tiny little pattern. And I moved it in a square, and the smoke was coming out, and so then I stopped the experiment, and I held the paper up, and I had carved a square, a perfect little square, 1/10 of a millimeter. And so I was like, great, I've got my own little laser cutter. But it's a really expensive laser cutter, so I didn't want to use it for that. So these are some of the practical things that you have to consider. And a rotational structure is not resolvable in liquids or solutions or solids, but it is in the gas phase. And so we will actually look at the rotation and vibrational spectra of carbon monoxide next week. So this week is just vibration of chlorobenzene and benzene. You're looking at the fundamentals. Next week, we take a diatomic molecule, carbon monoxide, and it's just one vibration, and on top of that is about 50 to 75 rotations. So we will see all of these different peaks related to the rotational modes of that carbon monoxide. And you'll assign quantum numbers to every one of those peaks. It's called peak picking. And it's easy, but tedious. So you'll learn about that. So remember, Raman is a 2-photon process. So we still have a fundamental transition, but the green laser light hits the sample, and a red shifted photon comes out, and the difference between those two is our fundamental transition. So we're still getting vibrational excitation. We're kind of going around about way to get there. The nice thing about this is this red shifted photon is still in the visible region. It's just a little less green than green. It's more towards the red side. It still goes through glass. I can't send IR through glass because glass has vibrational modes too. It's going to absorb all the infrared light. But I can send a visible laser through glass. So I send a green laser into the sample, and a red shifted laser photon comes out and is detected, and I take the difference in those frequencies, and I get the vibrational frequencies. So that's what's going on in the Raman spectrum, and that's why you can detect things at 900 wave numbers that the glass would totally absorb, and that's one of your discussion questions on the lab. How can you get a 900 wave number peak out of Raman when 900 wave number light is absorbed by glass? It's because you're not sending 900 wave number through glass. You're sending visible light through the glass and getting visible light out of the glass. And so the Raman effect can take spectra of things in glass. Infrared spectrum cannot. You could put that glass in the Bruker spectrometer, and it's just going to block all the light, and your detector is going to see noise. Now, Rayleigh scattering is most probable effect. You'll see a lot of green light if you were to look in the sample. And so that's just the elastic scattering. The Raman is inelastic scattering. I was happy with the test. So let's pause and look at the tests. We've got a few minutes left. I've been studying my video, so we'll see if we can. Okay. That's right. Mackenzie. Okay, sorry. Megan. Okay. Marissa. Okay. Taylor? Marcus? Okay, so I've got the, here we can